This is a video for AQA Further Pure Mathematics, section of Vectors 2.2, where we're looking at the vector equation of a line in 3 dimensions. Well, the fact that we've gone from 2 dimensions to 3 dimensions doesn't actually alter the form of the equation. It is still of the form r is equal to a, which is a position vector of a point on the line, plus lambda times d. So here we've got the point A, which is at 2, 4, 3, and the direction vector d is equal to I minus 4k. So we could write that the equation of the line R is the position vector of A, so that's 2i plus 4j plus 3k, and then add to that lambda times I minus 4k. Now, this isn't the only way we can write this equation. We could use column vectors, so instead of that we could write it as the vector 2, 4, 3 plus lambda times 1, 0, negative 4. And that is quite often a lot easier because we don't have to write out the unit vectors I, j and k all the time. And indeed we could combine this together in a single vector, so 2 plus lambda, 4, and 3 minus 4 lambda. R is simply the position vector of a general point. So if we take a point somewhere on the line, then R is its position vector, the form x, y, z. So x is 2 plus lambda, y is 4, and z is 3 minus 4 lambda. So for different values of lambda, R is different points on the line. Well, for the equation that we found then, the question says can we show that the point 5, 4, negative 9 lies on this line? Well, if we look at the x component, we have 2 plus lambda in the I direction. So if we want 2 plus lambda to equal to 5, then clearly lambda must be equal to 3. But we need to check then that this is also correct for each of the other coordinates of the point that we're looking for. So when lambda is equal to 3, r is equal to, I'm going to write it in column vector form, so 2, 4, 3 plus 3 multiplied by 1, 0, negative 4. And if we put that into there, when we get 2 plus 3 is 5, 4 plus 0 is 4, and 3 plus negative 12 is negative 9. So indeed the point that we want, 5, 4, negative 9, lies on the line. It's important that you check for all the coordinates and you don't simply say, oh, lambda equals 3, because that gives us the correct x coordinate. As with two-dimensional examples that we did, drawing a sketch is often a very good idea just to give us some sort of pictorial thing to represent. You don't need to try and do it a three-dimensional diagram, however. Something which is drawn on a paper like this is adequate, and then the vectors for A and D will be three-dimensional. However, if you've got nice use of graphics, as in a computer, we can look at a three-dimensional representation, as in this question here. We're asked to work out the line which passes through 2 points A and B. Well, as in the previous video then, to do this we first of all work out the vector for the direction, either AB or BA, it doesn't matter which. I'm actually going to work out BA. So remember that BA will be the position vector of A minus the position vector of B. So that is equal to 2, 4, 3 minus the vector negative 4, 2, and 1. And that gives us a direction vector of negative, I beg your pardon, of 6, 2 and 2. Once we've got our direction, then we simply need to pick a point on the line. We can use B or A, so it doesn't matter which one we do. And once we've done that, we can write down the equation. So in this particular case then, let's pick on A as being our point, so that we have that R is equal to the vector for A, 2, 4, 3, and then lambda times our direction vector, 6, 2 and 1. I beg your pardon, 6, 2 and 2. Now remembering that these are not necessarily unique, because 622 has got a factor of 2 that we could take out of there, we could say that R is equal to 2, 4, 4, and then plus mu times the direction vector 3, 1, 1. Well, the final thing we might be asked to do, as we were in 2 dimensions, is to work out the angle between 2 lines. So in this particular case, we would have 2 direction vectors for our lines, D1 and D2. The angle between the 2 lines then is found by using the dot product, so that we have that D1 dot D2 divided by the modulus of D1 multiplied by the modulus of D2 is cosine of theta. So for this example, we have that D1 is the vector 1, 0, 4, and D2 is the vector 1, 2, negative 1. I leave you to verify the following, but the modulus of D1 is root 17, the modulus of D2 is the square root of 6, and D1 dot D2 is negative 2. So therefore we have that cosine theta is equal to negative 2 divided by root 17 and root 6. Using your calculator then to calculate theta, it comes out to be 101.4 degrees to 1 decimal place, but we want the acute angle. So what's happened here is that although we've got our lines L1 and L2, instead of calculating the acute angle here, we've actually calculated this angle. So we need to get the acute angle by subtracting from 180 degrees. So the acute angle is 180 minus 101.4, which turns out to be negative, beg your pardon, not negative, but 78.6 degrees. Well, that's the end of this video. In the next one we'll be looking at three-dimensional lines in Cartesian form.